Okay, one thing we need to know for BC as far as differential equations are concerned is exponential differential equations and logistic differential equations. So an exponential differential equation is going to look something like dy dt equals ky. So things that you want to look for is this variable here needs to match this variable here, and it's only just some number times y. It also might say that the rate of growth is directly proportional to the population. And that is what this side here tells you. It's directly proportional k to the population y. Now with exponential equations, you need to recognize that if it looks like this, that means it's exponential, but it also means the solution looks like y equals ce to the kt. You can go through the process of separate your variables, integrate both sides, solve for y, but that is what you're going to end up with. So in this example problem down here, it says a population grows according to this differential equation. Now it's a different variable, but you just want to make sure the variable on top matches the variable in the equation, and it's p and p, so it does. So that means this is going to have the solution. Instead of y equals, it's going to be p equals ce to the kt. Now it says if the population doubles every 12 years, what is the value of k? So that's where you're going to have to, it feels kind of like you're making up your problem, but you're going to have to make up values that fit that data to be able to solve for k. So let's say initially your population is 1. That's an easy number to use. It says it doubles every 12 years. So that means in 12 years, your population is going to be double that, which is 2. So what that does is it gives you 2 data points that allows you to solve for C and then to solve for K. So you want to start with your initial condition first. So this is your T, this is your P. So 1 equals CE to the K times 0, which means you get 1 equals CE to the 0. Anything to the 0 is 1, so that just means C is 1. So we'll take that and plug it back in. And so now this is where you use your other point. So I'm going to take this in and plug it. So 2 equals e to the 12k. And so then you would have to solve that for k. So how do you get rid of e? Well, e and ln are inverses of each other. So you take the ln of both sides. And so that's going to give you ln of 2 is equal to 12k. And then you would divide both sides by 12. So ln of 2 divided by 12 gives you 0.058 if we round, and that is our value for k. So that's typically what you're going to see with your exponential differential equations, is they give you something that looks like an exponential differential equation. You have to be able to know what it's going to look like, and that's the y equals ce to the kt. Then you make up your points and solve for whatever you need. Now, a logistic differential equation starts looking the same way. So you have dy dt equals ky, ky, but then you have some sort of C carrying capacity minus y. So there were a couple things to remember here. With logistic, we're not concerned with solving it. With logistic, we need to know that C is the carrying capacity. So that may be like the maximum population that your land can support, or it could say like the population of a school is 1,200 people, so 1,200 would be your carrying capacity. So there was 2 things that asked you typically. So the first thing is the rate of fastest growth. And then the second was what is the limit as t approaches infinity for your population. So the rate of fastest growth will always occur when you have the carrying capacity divided by 2. So if your carrying capacity is 500, the rate of fastest growth is at 250. If your carrying capacity is 1,000, your rate of fastest growth is at 500. Then your limit as you approach infinity is always the carrying capacity. So in this problem down here, it says we have a number of moose in a national park. It's modeled by this differential equation. Now the thing is, it looks really similar, but this is not supposed to be divided by anything, and in this case it is. So what we're going to have to do is modify this a little bit. So we are going to factor out that 1 over 500. So that means we're like taking the 1 over 500 out of this one. We're taking the 1 over 500 out of this one. So since we're taking the 1 over 500 out of both of those things, that's going to mean you have 0.6 m, and then this 1 over 500 has been pulled outside. Now what that does here is it cancels the 500 and just leaves us with m, which is good news. That's what we want. We just want the variable by itself here. With this one, you have 1 over 500. Dividing by a fraction means you multiply by the reciprocal, so you just end up with 500. So now all of this part together is k. That's your what's in place of y. That's now by itself, so that means this is your carrying capacity. So it asks us here, what's the limit as t approaches infinity? That's just going to be 500. If it asked you when is the rate of fastest growth, you know your carrying capacity is 500, so it would just be 500 over 2, which would give you 250. So let me know if you guys have any issues with either of these two things.